Hi there. So in this video we want to talk about the basics of angles, and that might seem like a pretty straightforward topic, that you seem like you have some kind of intuitive idea about what an angle is, and I'm sure that you do, but we got to get into some finer details about them, and namely, how is an angle defined and how do we describe angles, and then we'll talk about degrees, how they're defined, but also breakdowns of degrees into smaller units called minutes and seconds. Okay, so the first thing we want to talk about is, what is an angle? All right, and so we have some kind of intuitive idea that an angle is something that looks kind of like this, right? And so we seem to have some intuitive idea, but what is the actual angle right there? Okay, so now, sometimes we draw a little arc to indicate an angle, so you might say that it's that arc, but make sure you realize you could draw that arc anywhere, and there's not a unique idea about saying what that arc is. Another idea is some kind of intuitive idea about maybe it being the space in between here. Okay, but that's an infinite amount of space, and so that's more area, and also that would be an infinite amount of space, so that won't get us anywhere we need to be either. Okay, and so we got to come up with some other idea. Now I will just point out the way Euclid defined an angle, and the way some classical treatments in geometry will is they'll treat these two objects right here as what are called rays. Okay, those two lines. So a ray has a starting point, and we'll use that in our definition of an angle. And then basically that it's a line that extends indefinitely in one direction, but has a starting point. So the way some people define an angle, it's actually composed of three things. It's two rays with a common starting point. And so an angle is just composed of those three things. And that's fine too. It just doesn't really capture the idea about how we measure angles, and that's what we're going to need. So the way we're going to interpret angles and work with angles is you can think about starting with this first ray right here, and we'll call that the initial side. Okay, like that. And so I'm going to just redraw this process here. And so we can think about starting with that initial ray, okay, like that. And then it's, in a sense, it's like we're going from this ray to that ray. So there's kind of a rotation that goes on. So what we can think about is rotating that array, in this case counterclockwise, and then stopping and producing this second ray. Okay, and so that's the idea. All right, and so the way we're going to interpret the angle in a lot of cases, the angle is a measure of that rotation. Okay, does that make sense? Hopefully. All right, and so now I will tell you that's one way to interpret angles. Like I said, there's more of the geometric way to interpret angles. All right, so there's going to be problems that we encounter where we're just working with some kind of geometric figure, namely a triangle. Okay, and in those cases, whenever we talk about the angle, we don't necessarily need to think about that as being from a rotation. We can if we need to, but we don't have to. But another set of problems in trigonometry arise from think about riding a bike here. Sorry, I can't draw very well, but all right, we have this person riding a bike, and what happens whenever you ride the bike is those wheels rotate, right? You crank the pedals and those wheels rotate. So you have this rotation going on, and the rate of that rotation determines how fast you move horizontally. All right, and so in those cases, keeping up with angles and their rate of rotation, and just their rotation in general, is really important. So there's just cases in geometry and trigonometry where keeping up with the rotation is important, and there's cases where we don't really need to worry so much about the rotation. But in order to have a clean working definition for a angle, we're going to look at it as a measure of rotation. One thing I almost forgot to mention, I'm kicking myself for it, but anyway, let's go back to this first picture right here. So it's just some important vocabulary. There'll be some important vocabulary throughout this. So where that rotation starts at, that's called the initial side, and then where that rotation ends at, that's called the terminal side. All right, and a lot of definitions are based on this vocabulary as well. So we got to keep up with that. So where an angle starts at is its initial side, where it ends at is its terminal side. All right, now before we start talking about specific numbers with angles, there's this notation of either a positive or negative angle. Okay, and so a positive angle rotates counterclockwise. Okay, and then I'll just go ahead and write this, you can guess. A negative angle rotates clockwise. Okay, and so if I wanted to draw a positive angle, I would start with my initial side, and then if you're really indicating positives and negatives, you need to indicate that rotation, and so that thing is rotating clockwise. Now notice I keep drawing that initial side horizontally, but I don't have to. I could start with an initial side right here. As long as I rotated that in the counterclockwise direction, that would be a positive angle. Okay, and just conversely for negative angles, I could start here with a horizontal initial side. Then if I rotate it clockwise, that's a negative angle. Okay, and again, it doesn't matter where your initial side is, so I could start here. Now make sure you realize the arc is indicating where you started, and that little arrow indicates where the rotation ended. And so what did I just do there? I was talking and not thinking though, and I drew myself a positive angle. So that would be a negative rotation right there. All right, so one thing to be aware of, there's two basic angle units we're going to deal with in this class. There is some other ones too, but one thing about angle units, since it's about rotation, they're defined or derived from rotations. Okay, and let me explain what I mean by that. Is the way we define degrees, we don't define what 1 degree is. We could, but the typical way we define it is we say 360 degrees. If you haven't seen that before, to indicate degrees, we just put a little O up as a superscript. So 360 degrees is equal to 1 full rotation. Okay, and most of us know that there's 360 degrees in a circle, but if not, that's okay. So 1 full rotation would be where you start with your initial side and you rotate all the way back around, and so the terminal side is the same as the initial side. Okay, like that, and so that's 360 degrees. Okay, now from that you can do some playing around. What would that mean that 1 degree is? Okay, well, one thing you can do to figure these out if they're not obvious is, since 360 degrees is 1 rotation, this is an equation, it has an equal sign, so I can divide both sides by the same number. So I could divide both sides by 360 to get 1 degree is equal to 1/360th of a rotation. Okay, now to really, so 1 degree is 1/360 of a rotation. Okay, now we can't draw that perfectly, but you could imagine going and cutting this circle into 360 equal pieces like that, and then your 1 degree would be right in there. Okay, so that's a very small rotation. That's an important thing to keep in mind. 1 degree is actually very small. Okay, so the idea is that I should be able to draw 360 of those little angles to get around to a full rotation. All right, and so once we have this basic notion too, we can get some angles. Some you might be familiar with, some you might not be, but you know, what's half a rotation? Okay, we have 360 degrees is equal to 1 rotation. Like that, we're talking about half a rotation, so I would divide both sides by 2 here, and I would get 180 degrees. All right, now if you think about the picture there, I'm starting here, I'm doing half a rotation, so I've just formed a line. Okay, and for that reason, people call these a straight angle. Okay, and likewise, 1/4 of a rotation would be even half of that, so that's 90 degrees. Most of us are familiar with a 90-degree angle. It's the corner of a room, basically. So we denote those with a square instead of an arc, and we call those right angles, like that. All right, be aware you might need to convince yourself of this, but 3/4 of a rotation Then a fourth rotation is 90 degrees. So to get 3/4, I would multiply by 3 here. And so I have 270 degrees. And likewise, we could do things for negative angles as well. And so if I wanted to talk about negative 90 degrees, all right, that's a fourth of a rotation, but in the clockwise sense. So I'd come back over here and I would end up with that. Now this is an important thing here. If you think about just about terminal sides, initial sides and terminal sides, we just got two results from one picture. Okay, what we just saw that this is negative 90 degrees, but in the previous slide we saw that this rotation is 270 degrees. Okay, if you take out the rotations and the rays, they form the same picture, and that's going to be important for later. If the rotation is important in whatever problem you're talking about, then these things are very different angles. This was way bigger than that. It also goes in the opposite direction. Okay, but trigonometrically, these two angles are called coterminal. Okay, because they have the same terminal side. All right, and so once we start doing trigonometry, the rotation's not as important. And so any two angles that are coterminal have the same trig values, okay? And so what I'm getting at here, this is getting a little ahead, but remember I've talked about the sine function a little bit, okay? That's a trigonometric function. And what we'll see later is, say I was trying to find the sine of negative 90 degrees, but I didn't know what it was. What we'll do is we'll do some work where hopefully you will know what the sine of 270 degree is. And since they're coterminal, you could rewrite that as the sine of 270 degrees and then get that. Now make sure you realize you can have angles bigger than 360 or smaller than negative 360. So let's think about this example right here. Here's a terminal side, and I'm talking about two rotations. So this goes around once and then goes around twice. And thinking back to, wheels on a vehicle, and while you're traveling, those things go through thousands of rotations. All right, so what's the angle right here? Well, first we had the first rotation. Okay, so that's going to be 360 degrees. Okay, but then I added on a second rotation, so I added on another 360 degrees. Okay, 360 plus 360 is 720 degrees, like that. Okay, so I could have lots of rotations. All right, and so let's think about what would be 4.5 rotations. All right, now you can think about this. Just think about this last picture. Or let's go ahead and redraw it. Okay, so here's our initial side. Okay, we do one rotation. Okay, so that's 360 degrees. Okay, and then I do another rotation. All right, that adds another 360, and hopefully you're starting to see the pattern. But I'm going to go 2 more times to get 4 rotations. Okay, like that. And then, but then I have another half rotation left. Okay, 4.5 rotation. So that's another half rotation. And like we said a minute ago, a half rotation is 180 degrees. All right, and so if you go and calculate that, you're going to get 1,620 degrees. All right, now also make sure this said positive 4.5 rotations. If we did negative 4.5 rotations, that just means that it would have rotated in the clockwise direction, and then our answer would have come out to be negative. Okay, now hopefully you saw the pattern there too. Whenever you have more than one rotation, you just multiply the whole number times 360. Okay, so the other way you could have done this, I'm sure some of you saw this and wondered, but I could have done 360 degrees times 4 plus a half rotation is 180 degrees. Now often we want to name an angle, so we'll have some angle and we'll want to refer to it maybe in general, or we don't know its value, and so we're going to want to try to use it as a variable to solve it. So one basic convention that some people use is they'll use capital letters like A, B, or C, etc., etc. Okay, it's not the most common notation to use for angles though, and it's not really what I use more often though. So we can use capital letters, though. That's one way to denote angles. But the thing is we often use Greek letters to denote angles. Okay, and so I'm going to show you some of the more common ones. The most common one is the Greek letter. It's a circle with a line through it, and we say that as theta. Okay, I will tell you that there's also script in Greek, and so some people will denote theta like that. Okay, and so there's theta, and then the first few letters of the Greek alphabet are often used. So that letter right there is called alpha, and I moved a little bit quick, but notice the way I did that. I started up at the upper right, and then you just swirl around to make an alpha, like that. The next letter is beta. It kind of looks like a script B. You start down here at the bottom, and you just make a smooth B, and so we call that beta. All right. The third letter is gamma. It's basically alpha rotated at 90 degrees, but also a little bit longer, so it looks like this, that, and we call that gamma. And another letter that's commonly used is a circle with a line through it, and I pronounce it phi. Some people pronounce that phi. It's strange, and this is just from my personal experience. It seems like more often in science and math, people pronounce it phi, but in sororities and fraternities, people mostly pronounce it as phi. Okay, and then also, we could use any Greek letter we wanted to. You can look up other Greek letters, but another commonly used one, especially when studying waves, is to use, it looks like a W, just a curved W, but that's actually the last letter of the Greek alphabet. It's called omega. All right. Another one that sometimes used that I'll refer to, I don't really use it a whole lot, but you make kind of a squiggly line like that and then make a line that goes down, and that's the Greek letter lambda. People use that often when describing waves, and they use it as a letter to denote what's called the wavelength. So all I'm getting at here is we may be looking at some situation in trigonometry, but we don't know the angles, but we want to denote them. So I might call that angle alpha, and this angle over here beta, and this angle over here gamma, or something like that. So, and again, just remember, often whenever we're just talking about a general angle, we'll use that. This is a very common letter to use, is theta. Okay, kind of a vocabulary term that we'll use quite often in here are what's called angles in standard position. Okay, these are angles that are drawn in the Cartesian plane. If you've never heard that term before, it's just the XY plane. Okay, and whenever we're drawn in standard position, the initial side is always on the positive x-axis, not just the x-axis, but the positive x-axis. Okay, and so just as an example here, if I wanted to draw 45 degrees in standard position, like that, then I would draw the XY plane. Okay, and then right here, this is the initial side. Okay, and then 45 degrees is half of 90. Okay, if you think about it, 90 degrees is a right angle, so 90 degrees would go right here to the positive y-axis, but we want half of that, and so we do a 45 degree angle. It would go halfway between there, and so there's 45 degrees in standard position. And if I wanted to give it a name, I want to call it theta. Just denote that theta is equal to 45 degrees. That's up to you. All right. And so, just another example. Say I wanted to do negative 210 degrees in standard position. Now, you might not know much about 210 degrees or even negative 210 degrees. But remember, the negative only tells you which way we rotate. So we're going to rotate clockwise, yes. All right. And so we go to here. All right. Now, in terms of negative angles, always remember the positive x-axis in standard position is 0 degrees. Okay. So I'm rotating I'm sorry, I keep starting to say that. I'm rotating clockwise. Remember, right here is the right angle, so that's negative 90 degrees. All right. If I continue on, that's a straight angle just in the negative direction, so that's negative 180 degrees. And see, I need to get to 210 degrees in the negative direction. All right, so that's just a little bigger than 180. If you think about it, 210 degrees is 180 degrees plus 30 degrees. Okay, like that. So what I'm getting at here is right here, I need to extend this rotation another 30 degrees. All right, and so 30 degrees is just a little bit beyond that. And so as far as negative 210 degrees goes, it would be about right there. And so then my terminal side would come out like this. All right, and so we a lot of concepts and problems are implied that you're using standard position, so that's an important vocabulary term to keep in your back pocket. All right, so a moment ago I said that 1 degree is very small, but it kind of depends on what kind of object you're doing a rotation on. And so on the Earth is roughly a sphere, and if you think about it, latitude and longitude are measured in degrees. And but on Earth, on the Earth's surface, 1 degree is about 57 miles. Okay, so that's actually a pretty large distance to be equivalent to. Okay, and so sometimes people that do very precise mapping, GIS kind of things, this is too big of a distance to be able to do accurate drawings and so on. So you need to be able to talk about units that are smaller than just 1 degree. All right, and it's kind of good news, but it also can get confusing. Is that the units that break down degrees even more are have the same wording as time, so minutes and seconds. Okay, and it's nice that the conversions are the same. We use 60s in both of those, but then it also can get a little bit confusing in terms of whenever you're talking about angles and time. So you just got to keep track of that in a given problem or in a given context. All right. So the breakdown goes that 1 degree is equal to 60 seconds, 60 minutes. I'm sorry, like that. And there's an abbreviation for minutes like there is for degrees. We put one tick mark up above it. Okay, like that. And so that says that there's 60 minutes in 1 degree. Now make sure you realize too, by dividing, we could also say that 1 minute is equal to 1/60th of a degree. Okay, like that. And then to break down minutes even more, we go down to seconds. So 1 minute is equal to 60 seconds. Okay, and if we want to abbreviate that, we can use two tick marks. Okay, and so that also says that 1/60th of a minute is equal to 1 second. Okay, so we do get that nice breakdown that works like time does. It's just we're talking about a different kind of quantity, an angle. All right, so now one nice property from this too that we'll use in a moment is that since 1 degree is 60 minutes and each minute has 60 degrees, that means if I want to go from degrees to seconds, think about this. How many seconds would be in 1 degree? Well, there's 60 minutes in 1 degree, but each one of those minutes has 60 seconds in it. So I would do 60 times 60, which is 3,600 seconds. Okay, like that. So we get that breakdown. Now, what that's going to lead into is two formats for expressing angles that have decimal parts. Okay, and so often an angle will come out to be like 20.14 degrees or something like that. So with decimal parts, and some people just use the decimals. Okay, and so that's called using decimal degrees. Okay, so that could be just writing an angle that has a decimal part is like 94.84 degrees, like that. But then some people use what's called DMS, which is an abbreviation for degrees, minutes, and seconds. Like that. So an angle would look like, let's say 64 degrees, 8 minutes, and 12 seconds. Like that. Okay. Now you might be wondering why people would want to do that. Just think about expressing a time. Sometimes with times we do the same thing in terms of hours. We might say something took 2.38 hours to complete, or some people might say it took 2 hours, 16 minutes, and 34 seconds to complete. Okay, so it just kind of depends on the context and how you're trying to answer something. And so we need to understand these two forms. And the main thing we want to get down right now is how to convert between them. If we're given one form, but we want it in the other form, how do we do that? Okay, so the easiest conversion for me to do, and we'll need this at times as we do some trigonometry with decimal angles, is if you have an angle in DMS, how do you get it into decimal degrees? And you just got to remember the fractional parts of each one of these. Okay, now first of all, decimal degrees, we're mostly just talking about the decimal part. And the decimal part comes from the minutes and seconds because those are parts that are smaller than 1 degree. Okay, so as far as the whole number goes in the degree, the decimal degree, it's going to be those 64. Okay, but there's a part that's added on for the decimal part, and the first part is this 8. Okay, but each minute is 1/60th of a degree, and so what I have right here is 8/60ths. Okay, and then plus, then I have these 12 seconds. Okay, remember what I said, there's 3,600 seconds in 1 degree. So we divide by 3,600 right here, and then that will convert that all to degrees. All right, and so if I go and calculate that on my calculator, so I'm just typing in 64 plus 8 divided by 60 plus 12 divided by 3,600. All right, and so I get 64.13, and then I have a 6 that repeats. And so remember that mathematically the way you can express something that repeats is to put a bar over it, degrees. All right, and so that would be the angle in decimal degree. All right, and so in general, if you want to go DMS to decimal degree, all you do is you type in the degrees plus the minutes over 60 plus the seconds over 3,600, and that gives you the degrees right there. All right, now to do the other, we go just the opposite direction. So we're going to start with a decimal degree, and we want to get that in DMS form. Now, one thing about this for me is whenever I assign problems where we have to find an angle in degrees, I always tell you to give it in DMS form, but our calculators will start out giving us in decimal degrees, so we got to know how to convert to here. Okay, and so let's look at that example I wrote a minute ago. I had to look at it, but it's 94.84 degrees. Okay, now first of all, in terms of the degrees, so remember with DMS, I want to give the number of degrees, the number of minutes, and the number of seconds. Okay, but this is the number of degrees. Okay, and so we have 94 degrees, and then we have this plus 0.84 left over. So this is where the minutes and seconds are going to come from, but this will give me my degrees. So for now, all we have to do is mess with this 0.84 degrees. And so what I want to do first is get the number of minutes. So I have 0.84 degrees. Okay, if you think about it, we're doing the reverse process of what we did in the last problem. Okay, this time in the last problem we started with DMS, we went to decimal degrees. Now we're doing just the opposite. We're going decimal degrees to DMS. So it makes sense that you do just the opposite. In this method we divided by 60. So here, hopefully it makes sense that you would multiply by 60. You could also do some dimensional analysis if you know how to do that you have 0.84 degrees. So to get the degrees to go away, I need them in the denominator, and I want to get minutes in the numerator, and 1 degree is equal to 60 minutes. And so the degrees cancel, and you do 0.84 times 60. Okay, so we do 0.84 times 60, and we get 50.4. Okay, so again, remember with DMS, we're trying to get whole numbers for these. And so this is the number of minutes, and then the number of seconds is going to come from the decimal part of that. And so we have, so far, well, let's just start writing the answer. We have 94 degrees and 50 minutes, okay? And then this is 50 plus 0.4, So this is where I'm going to get my seconds from. And how am I going to convert that into seconds? I'm going to do the same thing. I'm just going to multiply it by 60. All right, you do 0.4 times 60, and we get 24. Okay, 24 seconds. All right, and so that would be that angle in DMS. Okay, so the outline of this procedure, if you're going from decimal degrees to DMS, is the whole number will be the number of degrees. Then you take the decimal part and multiply it by 60. Just get the whole number version of that, and that gives you the number of minutes. And then you take the decimal part again and multiply that by 60 and get the number of seconds. Now, often it just kind of depends on what you're being told to do or what you need to do once you're out there working. But sometimes the seconds will have a decimal part too, so they'll come out to be like 22.8, like that. What I always do, since seconds are so small, I always round to the nearest whole number seconds. Some people will go ahead and write the decimal part as for the seconds, and I don't really mind if you do that. But I always once I get to the seconds, I always round to the nearest whole number of seconds. All right, so that's just a quick overview of what angles are, and then how we deal with them in degrees. There's going to be another type of unit for angles called radians that we'll talk about later in the course. They pertain more to analytic trigonometry. But when people are out there actually measuring angles, they usually measure in degrees, and they do often break down into minutes and seconds as well. I have several maps that I use that break them down into minutes and seconds, and it's fairly common. All right, so I hope that helps. Let me know if you have any questions, and all the best.